All right, I'm back. We're on the bottom of page 260, and we're going to do a problem that's actually a very common type of problem, and you got to get used to writing up your answers to these sorts of things. So they're not usually too difficult. It's the details that you really need to nail, and that's something in math that you're probably not used to, where like it's the way you write it that matters, not necessarily what you write. So let's see if we can do this. So we want to determine the values of a and b that make the function f of x, shown below, continuous. So you'll notice immediately, like, there's a lot of piecewise functions when you start doing limits. It's because it just makes it more interesting. Like, you can take a random thing and a random thing, and with piecewise functions, put them together, make the limit exist, make it continuous. That's what we're going to try to do here. So we need to remember the definition, and it's 3 parts. So we need one. We're going to need the limit as x approaches c of f of x to exist. We're going to need f of c to exist. And we're going to need the limit as x approaches c of f of x to equal f of c. So those 3 things are going to need to happen. This exists that I wrote here, crazy. Also, it exists. All right, so we need this to be true. This function has, so look at the pieces, right? So by itself, a times e to the x plus 1 is continuous. So the only place that we could have a problem with this function is at 0, because that's where we're arbitrarily breaking the function apart and we're going to start a new function. So that's the only place of interest for that part. And then inverse sine is also continuous everywhere, right? We know what inverse sine looks like. It kind of like this, assuming that I mirrored correctly for you. So that's going to be continuous. So the only problems that could have are at 0 and 2. And then polynomials are continuous everywhere. So the only place that could have a problem is at 2. So it's all of the breaking points for these piecewise functions are really the issue. And that sort of generally is the case. Piecewise functions tend to have issues at their breaking points, not everywhere else. So let's see. Let's deal with 0. So I'm going to say here, deal with x equals 0. All right. So I need the limit. If the limit's going to exist, I need the limit as x approaches c from the left. Oh no, not c. 0. Limit as x approaches 0 from the left of f of x to be equal to the limit as x approaches 0 from the right of f of x. Okay, so that's for the limit to exist. So if you look back at your definition, which you probably have in front of you, I have it in front of me on a different computer, so I'm just going to use it. If I am to the left of 0, I'm supposed to use a e to the x plus 1. So the limit as x approaches 0 from the left of a e to the x plus 1 should be equal to the limit as x approaches 0 from the right of, so f of x when you're to the right of 0, when you're immediately to the right of 0, is sine inverse of x over 2. So you're going to have to remember your sine inverses, but that's probably not a problem. All right, so continuous function, the limit equals the value of the function, which means I can actually evaluate both of these limits by just using substitution. So this will be a e to the 0 is 1, so it's a plus 1 equals the inverse sine of 0. The inverse sine of 0 is 0, right? Because the sine of 0 is 0. So this will be 0. So now I know that a equals -1. Okay. I also need so I also need f of, what is it? I'm going to add it up here. I also need this equal f of 0. But by definition, because of the way that the function is defined, at 0, I'm supposed to use this definition. And so this is equal to f of 0. So we've done it. We've dealt with x equals 0. We made it continuous there. As long as a is equal to -1, it'll be continuous there. Now we've got to deal with 2. Whew. All right. So deal with x equals 2. And we're going to do the same thing. I cannot write deal. Look at that. It looks like I wrote dead, but I spelled it wrong. All right. I need the limit as x approaches 2 from the left of f of x. So we write it out using like function notation to equal the limit as x approaches 2 from the right of f of x. And I need both of those to equal f of 2. That'll make it continuous. That's like the definition. So now I'm going to work out what's happening. So immediately to the left of 2, I use the arcsign definition. So this becomes limit as x approaches 2 from the left of sine inverse of x over 2 equals immediately to the right of 2. I'm supposed to use the polynomial, the limit as x approaches 2 from the right of, so that's x squared minus x plus b. Okay, so now both of those are continuous in and of themselves, which means that the limit equals the value of the function. So I'm going to evaluate the limit by finding the value of the function at 2. So this will be the inverse sine of 1. So what gives you that? Think about that. Think of the unit circle. The y value. So it's up there. It's pi over 2. And then here, I just evaluated 4 minus 2 plus b. So pi over 2 equals 2 plus b. So if b is equal to pi over 2 minus 2, this function will be continuous. We will have forced this to happen. So these are my values. So I'm going to underline them. If a is this and b is this function will be continuous. So really when you're doing this, you really focus in on the limits. It's the limit from the left equals the limit from the right. Limit from the left equals the limit from the right. The value of the function will work out because of the way the piecewise function is defined. The only thing that could have happened here is maybe 0 and 2 aren't in the domain. Like they're not accounted for by branches. And then to make it continuous, we would have needed to add a separate branch for each of those and just said f of x is equal to, what would it be? 0, I guess, when x is equal to 0. And where am I getting 0? So I did -1, e to the 0 plus 1. So -1 plus 1 is 0. So I would have added that branch, and then I would have added, I don't even want to work it out. Oh, well, I guess it would be 2 plus, what is it? Just pi over 2, I think. 2, so f of, man, hold on now. So f of 0 is definitely 0. F of 2 is going to be x squared, so it's 4 minus 2 plus, I don't know why I'm having trouble with this, pi over 2 minus 2. So pi over 2. I may have said that at some point. I also may not have said that at some point. But if we use these values, we'll get a continuous function. What I'm going to do now is, and you could dip out of this if you wanted to. I'm going to switch over to a calculator. So let me open up a calculator that I can switch over to. I'm going to switch over to the calculator and just graph this thing, right? So I think we are not yet seeing it. Okay, so now I think we're seeing the calculator. There's some calculus stuff on here. Don't worry about that. I'm actually going to start a new problem. And I'm going to go to a graph page. And I'm going to use a template. And I'm going to choose a piecewise function. So it's got to have 3 branches. 3 branches is like the default for 3, but you can choose whatever you want. 3 branches, so it's going to be negative. I use exp to the x, but you should use the e to the x key, which is over here, plus 1. And that's when x is less than 0. So less than, all of those are control equals, but I will just be typing them because it's so much faster. But control equals will take you to that. And you should know that, so make sure you do. Arcsign, so I'm typing arcsign, but it's the same as using sine inverse. 0 less than or equal to, you can actually type that on the keyboard, and then less than or equal to 2. And then x squared minus x plus, so we got pi over 2 minus 2. And that's going to be when x is greater than 2. I could leave this empty, and it would just fill in the remainder. It would actually say else there, but I'm gonna, for the completeness of it, to make it look exactly the same, I'm gonna do this, and I'll press enter, and there you go. It's not a nice looking function, but it's continuous. So imagine we had gotten it wrong. Imagine that we thought that this was supposed to be just pi over 2. Sometimes this still almost looks continuous. Let's see. No, broken. Definitely wrong. So let's put this back. -2, I think it was. On this end, what if we had gotten the coefficient wrong here? Say we somehow thought it was -2. Broken, right? So the only values that work in this case are a is -1, b is pi over 2 minus 2. We got those by evaluating the limit from the left and the right at each of those breaking points and setting them equal, because for continuity, the limit needs to exist, needs to equal the value of the function, and that's what we made happen. So I'm gonna go back to the notes because for some reason I like to be on that when I end a video, but otherwise we are definitely done with this. And here they come. And all right, I will be back in the next set of, no, in the next page, in the next video, I'll be back is what I'm trying to say. And we're gonna keep going. So I will see you then.